Hi, my name is Bart Haar Romeny, and I go give you a gentle introduction to Mathematica, the new Raspberry Pi 5. Okay, let's start. We go look at Mathematica, so let's have a look if Mathematica is installed. Yes, Mathematica is installed. If it's not, you can just look at Preferences, Recommended Software, and then it checks what packages are available. And then in the Programming section, you see Programming Mathematica. Just make sure this box is ticked, and then you click Apply, and it will all install. We need a notebook, and we go first download this notebook by opening a browser. We see that we open the Wolfram.com Raspberry Pi website, and we see that Wolfram Language and the Mathematica is free on every Raspberry Pi. That's really nice. So we go download the notebook, and we do this by going to romeny.ai, my website, /nb for notebooks, and this is called intro.nb. And you see to the right here that yes, it is downloaded. We can close this window, and we go have a look now with the file manager in the downloads section. And yes, we see that we have downloaded the notebook intro.nb. Let's open it with, and then we see Programming Mathematica, and now set the selection application as default action. If we do this, then every notebook we can just double click and start it. So now Mathematica opens, and it loads the notebook. You see we also get a welcome screen. The welcome screen has the Wolfram Language Documentation Center. If you click on it, you see the large range of the Wolfram Documentation Center with visualization and graphics, data manipulation, symbolic and numeric computation. We go study quite a few of this. Let's keep this now for later. You also see the Wolfram and Raspberry Pi website that we just saw, and there's a Wolfram community, and there you can ask all kind of questions. There are thousands of Wolfram Mathematica users, and you can find many answers to your questions right here. Okay, let's look at the notebook. We see the notebook right here. Let's put this behind it. This notebook is a gentle introduction into Wolfram Mathematica for the Raspberry Pi. You see it is a lot of stuff that I like to introduce you to. Introduction, we go start with some plotting, how we can manipulate everything that we code, how lists are dealt with, etc. So here you see a number of things. In the description on the YouTube movie, you find the starting times of all these sections. If you want to make this bigger, if it's not readable, then you can, to the lower right, make this, let's say, a little bit bigger, or press Ctrl, and with your mouse wheel, you can just make this any size. Let's make it like this. You see that we have here all kinds of different fonts. We have images, and we can use all of these in so-called cells. Here you see a cell, and this is another cell. And on the top you see that the cell has the type of text. And there are lots of different section cell and input cell. Input is where you put the code. And this input means input to the kernel that will actually calculate the code. Okay, let's open the introduction. And the best way to learn Mathematica is by seeing it and by doing it. So I invite you to download this notebook and do everything that you see here. And I only give you pointers because there are so many possibilities, but you just need to know where to find it. It will take just a couple of hours. If you read a couple of these notebooks that I have on the website here, then you will quickly grasp the style of programming and the notation, the functions, the style of programming. It's all really intuitive, and it's all in plain English. There are no abbreviations, and there's very carefully naming of all the functions and programs. So now you can write anything 21st century style. You can include images, you can include whatever you like, hyperlinks, video. It can all be included in the code. you also do not have to search for images anymore, for packages anymore. That is another language is quite a pain, and they have names that are really not logical, but everything is included. Mathematica is a big program. It's 1 gigabyte on a Raspberry Pi. And if you download it with the full documentation on a Windows or a Mac system, it's about 5 gigabyte. But then you have it directly. And of course, on a laptop, you have a faster system, and you also have a GPU. But the Raspberry Pi 5 turns out to be quite a nice hardware to run Mathematica on. It's fast. It is programmed by very professional programmers who took great care to make all the functions as fast as possible. They're beautiful visualizations, and you can do any math that you like. And we go look what is functional programming. And remember, a Mathematica notebook is just code. It's a 21st century computational essay, so you can really use it as a document, send it to your colleagues or friends, and anything, formulas, hyperlinks, whatever, can be included. So never write a comment section anymore, but use text cells. So this cell here is just a text cell, as you see in the upper left. This comment style is really from the 90s, from decades ago. It's very early, and it reminds you to what I said, previous century primitiveness. Okay, let's have a look at the first action. Here we see the plot command. Plot the function sine of x for t running from 0 to 6 pi. We see a couple of things. Let's first do it, and we press Shift Return. First time it takes a little longer because the kernel has to be loaded, and you see a beautiful plot of the sine function. If you move your mouse, you see the x and y coordinates nicely, what are the values locally there. All functions in the Mathematica library begin with a capital. So plot here is a function that comes from the Wolfram system. Sine is a system command. And all functions have square brackets. So you see the sine has a square bracket of t time. And this is a list. It's a group, a set. That means it groups t from 2, from 0 to 6 pi. And the pi is interesting. If you want to type the pi, let's do it. You take escape, that's the upper left key on your keyboard, P, escape. So this is how you type exotic fonts. If you type escape A escape, you get the alpha. If you type escape capital P, you get a capital pi. Or escape W, you get omega, etc. So this is the way to make mathematical commands. There are a few other ones. Escape inf from infinity, you get the infinity symbol. Okay, so now we know how to enter the first command. And I listed here a little bit how you do that. This small thing, the escape character that I showed you here, you can type it as backslash square bracket escape key square bracket close. So if I do it right here, and you see where I click, I get a horizontal line, and you see to the left this plus here. That means you can now enter anything, and default is the input style. If you want something else, you just select here another type of cell. But let's do an input style, and if I type backslash this escape key and then this, oh sorry, there we have it. Okay, let's make this a little bit more beautiful. So after this list, we can add some things that we called options. Let's say we wanted to make it filling to the axis. So we just type filling and then minus larger than. So if I type it with a space, it's minus space larger than. But of course, if you remove the space, then you get this. And now to the axis. This option is now taken, and now you see I really nicely get filling to the axis. If you want the filling style different, for example, you want the filling style yellow, you just say filling style and make this yellow. So it's really simple. If you want the plot style, and this is the plot, this is the filling, and that's the plot. So if you add, let's say you want the plot style, and how do we want it? We want it, let's say, red, and we want it dashed. So we say we make it red, we make it dashed. But now we see we have a group here, red and dashed, and a comma cannot exist alone, so we have it in a group. So we really make it into a list, and we say there are two commands here given to plot style, red and dashed. And now you see we nicely have it. We have a filling style, we have a plot style. If you click with your right mouse here on plot and you ask get help, then automatically a browser window will start. And you see, oh, this is the legacy documentation. We have 13.3 on our Raspberry Pi 5, but we have the current version, that's version 14. I expect soon 14 to come on the Raspberry. But here we see how plot is organized. Make this a little bit smaller so we can see. So plot gives a function and then x from x minus to x maximum. And this is exactly what we have used. You can also use multiple functions, so f1, f2, etc. Let's have a look at what examples do. And you already see this is the example that we took in our example. And here we have an example with multiple functions. And you see copy to clipboard. If you highlight the documentation, and you click, it's copied. So let's have a look. We Control V and we paste it here. We change this pi, and you see pi is with a capital, so this is now the official pi from the system, but we make it escape pi escape. And now we see that we have three functions copied from the documentation: sine x, sine 2x, and sine 3x. Remember that there is between here there's a space, and that means that the space is in multiplication. So that's really different from x3 or no, this is 3 times x. From 0 to 2 pi, and the option is plot legends to expressions. It automatically reads then the expressions, no matter what they are. So let's see what it does. And now you see we have nicely the three functions, sine x, sine 2x, and sine 3x. The green one, the orange one, and the blue one. This documentation is incredibly extensive, and I invite you to have a look. You can do the filling to the bottom, as you see. If you have two functions, you can easily say do the filling from 1 to 2. Many functions, and if you want to see what options are there, just open the options, and you see there is an incredible amount of options. There are 128 options. You can change the background, the image size, you name it. Have a look and play with it. The documentation is the most extensive documentation ever made. 150,000 pages. And everything, copy, paste, this whole documentation is in Mathematica notebook. So you can copy any example here and use it directly in your own text. Okay, one thing that I didn't mention, if you want to add, for example, the pi, you do it with escape p escape, but there's also a menu function here, it's called palettes. And this top one is the basic math assistant. And here you see it, the basic math assistant. And this gives you all kinds of things that you can just click. So if you put your mouse right here and you click in the basic math assistant and you say I want infinity, you get infinity. It becomes nicer if we can manipulate the function. Manipulate means make it fully interactive. What we're going to do is we're going to change the amplitude, call it alpha, the frequency omega, and the phase. So we do that here. We write the plot function, alpha times the sinus, omega t plus phi. Let's run it first. And now you see that this manipulate function creates an applet. And this applet, let's make this a little bit bigger, has a plot range of -3 to 3, and that's fine. We have here the range from -3 to 3. And there is a slider for the amplitude, omega, and phi. And why do we have the slider bars? Because here we have set alpha goes from -3 to 3, but alpha has a little bit extra. And you see it's between curly brackets. It starts at 1 and it has the label amplitude. Omega runs from 1 to 3 and phi runs from 0 to 2 pi. And again we have the notion alpha, we indicate that as escape A escape, omega as escape W escape, and phi as escape F escape. And shift return runs this. Now we can change everything interactively. Open the plus and you see what is the value of the parameter. Here we increase the amplitude, it becomes 0, and here we make it negative. So you see we go from positive to negative. If we change the frequency, we increase the frequency, and we can see it right here. We can even make a movie and then it will run automatically. You can make the movie forward, backwards, back and forth. And also, of course, you can export this as a movie in MP4 format, whatever you like. You can stop it. And this is the phi, and phi is the phase. You see, we can change the phase, shift it of the period. So that's really nice, and we can put everything here in the manipulate. To show that, let's do an expand of x plus 1 to the power of n. And n, you see, the manipulate, everything with capital letters, manipulate with a capital letter, expand with a capital letter. And this is the iterator, that's the set, n, the list, n runs from 1 to 100. But now it's important in steps of 1, because if we take here a fractional number, it doesn't work. So let's see what happens. If you show n, and we make n, for example, is 2 or 3, 2, this you can do by hand, etc. But now you can do this. You see how fast it is, even on the Raspberry Pi. You can make really fast polynomial expressions with this. So n runs from 0 to 1, from 1 to 100. But the nice thing in Mathematica is that you can play. You see these coefficients here, and they get bigger and they get smaller. Can we visualize them to see how they behave? Well, what you need to do is extract the coefficient list. It's exactly what it is. Coefficient list. Coefficient list. We do that from the expression expand. And what we do, we take them from x. And now we get the coefficient list. And you see, okay, I have 1, 36, etc. Now we have the whole list. Interesting, but not yet so visual. So let's make it a list plot. So we just say list plot, and now we have the closing bracket right here. And now you see, for low end, it's not so interesting. Hey, this is really nice. So the bigger it gets, the more it gets closer to a normal distribution, to a Gaussian function. And that's exactly what it is. If you go to infinity, it really is the Gaussian distribution. And this playing around with Mathematica is why I like Mathematica so much, that anything you like to see halfway your reasoning, you can right so do it. In the next section, we go look at lists. Lists are key notions in Mathematica, as they can represent anything: numbers, data, expressions, images, etc. And many functions work on lists. Let's have a look. Let's make a table of exponents, x to the power of n, and n runs from 1 to 10. shift return, and we get the list, and you see nicely the whole set, enclosed in curly brackets. And now we can do many things on these lists. We do reverse on a list, we get the length of a list, we can take part of list number 1, and this is, of course, this happens so often that we have double brackets for this, and the double bracket you make escape, bracket, bracket, escape, and then escape, bracket, bracket, escape. So double bracket are entered with the escape, like we also did the Greek letters. So now we see we have list number 1, etc. That's X. And that's the same because it's close to English as the first of a list. Of course, you have also the last of a list, but first on a list, you can also write this shorter, at first at list. So this is a short form of the same square brackets here. So if I ask now for first of lists, you get, of course, the first one. What happens under the hood? Well, you want to see how this list is made. We make use of full form. So let's see and now we see what is really inside. X is just there, but the second one, x squared, is known as power x, 2. So this is the symbolic representation of x squared, x to the third, etc. And all of them are embedded in lists. So this is what you call the head of a function, and this is the head of that power function. So inside we all have heads embedded in this list. If we take a random sample of the list, we just shuffle them and we get 5 of them. You can also make lists not with the table function, but with several functions embedded. So here we see the function random integer, and this takes an argument from 0 to 99, just integers, and then 4 rows and 5 columns. You can make this as high dimensional as you want. Then you make not matrices, but in this case, but you make a tensor. And if we have random integer, let's just take it out, copy, and take it in a new cell. You see I have the square root here. If I press with my mouse and I take Control 2, you see I get the square root. So with Control you can make square roots, Control 2. Let's see what this does. You see I get a lot of square roots. Here I get 2 square roots. So it's not easy to see. So because it is a double list, this is the first row, that's the second row, and of course we have it here. If we make it into matrix form, that's much easier. We can do it like this. If we want to extract a particular element on the third row, fourth column, we just say double bracket 3, 4, we get this one. We can also use a range, and semicolon is the range operator from 2. So this means from 1 to 3, comma, from 3 to 4. And I show it as a matrix form. That's easy. You can also say, if it's close to English, use take. Take from the list M, the rows 1 to 3, and the columns 3 to 4. And show that as matrix form. It's exactly the same. You see there are multiple ways to do that. If lists are very big, you have to be careful that they are not output to the screen, and you use just a semicolon at the end. So I put here a semicolon. Now I make a random real, numbers between 0 and 1, 1,000 rows and 1,000 columns. So 1,000,000 entries. And then I ask for the dimensions of this matrix. Okay, it's 1,000 by 1,000. Summing them all up, I could sum them all up, but then summing runs only for row by row, and if I want to do one level deeper, I say, okay, the level is now not level 1, but level 2. Now I get the total of all the elements, and that's 500,000. The inverse of this matrix is calculated really fast. It's quite a complicated calculation. So let's do the inverse. You see I have a semicolon here because I don't want 1,000,000 numbers to the screen. The inverse is just as big as the input matrix. And I ask for the timing. Let's see. Okay, less than 2 seconds, and that on a Raspberry Pi 5. That's quite nice. Remember that this can only be done by real numbers. If you do this for integer numbers, it's far too complex, and even on these big computers, you cannot do this. So what did we learn so far? Lists are in curly brackets, can be nested as often as we want. Elements of lists are with double square brackets, escape, square bracket, escape. A semicolon prevents output to the screen. Functions can work on all different levels on a list, and it's always plain English. Make a table, take some data, take the inverse, do matrix form, etc. Now let's do a tiny bit of image processing. Images can be used directly in expressions. That means you can use them in your code. You can import them in your code. I have them here, an input in an image rotate function. I rotate over phi, and the surrounding must be all that is needed to rotate the image. And I manipulate it from phi to 2 pi. So shift return, and now we see the all means that there is a black surround, and if I now rotate my image, you see I can easily rotate my image. It's plain English. Manipulate, image rotate of the image tiger over the image phi, make the surrounding so that it covers all of the image, and phi runs from 0 to 2 pi. You see the curly brackets for a list, you see the square brackets for a function, and if we want to input the image, for example, I want to change this image, I can take another image, I can open the browser, and let's say I go search for tiger. Okay, I look for images, and I got lots of tigers here. Okay, let's take this tiger. That means I say copy this image I delete, and I say Ctrl V, and now my image is right here. And now if I rotate this image, you see I have now another image that I can rotate. It's very easy to import images from whatever, whatever other program. You can use images from the documentation. This is a test image on the house. You can very easily import images just by specifying the URL, so the internet address. And now it directly reads it, and here you have the image. Any image can be easily imported. There's so many functions to work on images, and this is just an introduction. Here you see that we have lots of images, image mesh, image multiplier, image bounding boxes, image capture, image position. Anything you like to do with images, please search it out, and there will be many notebooks coming that specifically work on images. It was my field for many decades, for many years. If you want to see the dimensions, you use, for example, the image dimensions of the tiger. This function now speaks for itself. I take a sub-image, and that means image take from the image tiger, and then I manipulate the row from rows plus x size, and x size is of course the x size in the x direction. X size runs from 1 to x dim in steps of 1, and the initial value is 100, and the same for y size. I have rows and columns, and I have now 4 items that I manipulate. So let's see. I make the sub-image, and here we have it. And if I now make the size bigger, you see, you can take the size, you can change the columns, you can change the rows. And to make a sub-image interactively is just a matter of specify one line. You have an interactive image selector. Image take is, if you don't specify this one, image take is clever enough to remember that it should be integer pixel positions. Here we have an interesting one. There's a website, thispersondoesnotexist.com. Each time when you call it, it generates a random face. And you can just import the face from the image by saying, okay, from this image I want the image, and you make a table, and you do it 9 times. You see, we have here an iterator, that's between curved brackets, and we make it into an image collage. Let's have it do it. Collaging means that it makes a nice stacking of the images, and here we have them, really nice. So you see, it's fast, it's very flexible, and it's again plain image. Make a collage of a table of imported images from this website. And what you import is the image. You can import all kinds of things, HTML, XML, etc. Anything you want, you can do. If you really have big images, and this is a big test image, it's called volubilis, and you see it's 9,000 by almost 4,000. There's a viewer, it's called dynamic image, and if you show it, you see we have the image here, and we can now zoom in, and zoom in actually quite fast and quite nice. And no matter how big the image is, you can easily now do a quick survey of the image. It's just a very tiny introduction. As I said, a gentle introduction. There is a lot in the documentation. Image processing, you see we have version 14 now, but this is 13.3 for image analysis. It's very much the same. And just have a look. Creating and importing images, image properties, image measurements, type, histogram, all kinds of statistical operations, the median, the quantile, the variance, image adjust for brightness, contrasts, gamma size, gamma, image compose, image assemble, color manipulation, geometric operations. You can do all kinds of image transformations, morphological image processing, opening, closing, filtering, correlation, convolutions, Gaussian filtering, feature detection, automatic face detection, feature tracking, remove the background, binarize, watershed. It's a lot. Just have a look. And there is also a whole set of tutorials, and these tutorials are really nice. They take you step by step by the hand in doing all kinds of things with these images. It's the best way to learn it, by doing it. It's time to take a small break and tell you a little bit of some handy functionalities and some tips. If you worry that your notebook gets too big with all these outputs, you have lots of images and tables and so on, you can delete all the output. You go to the cell menu item and you say, okay, delete all output. And now all output is deleted. If you are, and then if you say, hey, my output is now gone, you can run the whole notebook by evaluation, and then you just say evaluate notebook, and you run everything, and all the output is, for example, by the receiver. If you send a much smaller input, much smaller notebook to someone, you can easily generate the new output. If you want to find matching brackets, press Control Point, Control Dot. It's very easy. Then if you have a long statement, you go to Control Dot and you see bracket to bracket that match. An interesting one is what is happening inside these cells. For example, I have a speed, and this is a subsection cell. You can press Ctrl-Shift-E, and to see what is inside this cell, E for expose. And you see the cell has this string speed. It's a subsection cell, and it was changed at those times. If you press Ctrl-Shift-E again, you get it back. This cell, Ctrl-Shift-E, shows that it's an item paragraph. And this one, you see, it's a row box and a grid box, etc. You don't need to know all these things, but now you can see what happens here. If you want to do some tiny adjustments to a cell, you can do it here in the internal representation. Ctrl-Shift-E brings me back. If you close the groups of cells, as I do here, you just double click and all these cells are closed. And now you see you get a very tiny hook on the bottom of these cells, and double clicking again, you open them. It's very handy to make a nice overview of your document. About speed, always be careful that Mathematica is fully symbolic and that all your operations are in principle symbolic unless you say they should be just numeric. If you have this integers, for example, and you take the inverse, it makes the complete inverse, and if you take the eigenvalues, it does it. But if you make this much larger, it becomes very difficult to do this analytically. But if you do it on real numbers, I showed you this before for the inverse, if we take a 1 million entry matrix, you see it's now random numbers between 0 and 1, 1000 rows, 1000 columns. And the dimensions of this matrix, it's 1000 by 1000. It's a dense matrix, not even a sparse matrix or really every item of the matrix is filled. Well, do the eigenvalues, and even on a Raspberry Pi, it takes just 5 seconds to calculate 1 million eigenvalues, and that's really nice. There's, of course, some differences with Python. Mathematica follows the classical historic definitions, that the brackets are only for equation grouping, so these are not for functions. And the plus is for numerical addition, and not to join strings. To join strings is with this command, smaller than, larger than. So if you add these two strings, you get the strings together. You see camel case, that's the way in Mathematica how the internal formulas, internal functions are mentioned. The dot is not for an object attributes and methods, but just only for the inner product. So I have a small vector here, ABC, and it's the dot product with another vector. And here you get what you call the dot product. And everything is an expression. And that means you can do so many things. You load images into your code. You load all kinds of formulas in your code. And we have functional programming. Another difference with Python is that list runs from 1 to n, not just from 0 to n minus 1. So if I count the fingers of my hand, it's just 1, 2, 3, 4, 5. It's so much more intuitive. And the zeros element of an array in Mathematica is simply the head. So if I have this list here and I ask for the 0th element, you see it is list. If you ask for the second element, you get, of course, you get a B. And Mathematica is incredibly complete. There is no need to search for packages. And in Python, they often have names that are not easy to find a package with that name. You have to search in all kinds of web pages. And in Mathematica, it's very often, no, it's always the real name as it is used in the scientific field. Okay, it's time to do some graphics and visualization in Mathematica on the Raspberry Pi 5. This is a very important and powerful tool in Mathematica. And to create graphics, you need primitives, and they're all present. And first, what we do is we open the command graphics, and then you say, okay, what do I want? I go draw some points with arrows between them. And you first take a red pen, and you say, okay, what I draw is dashed. Then you make a table of arrows. Let's first actually draw it, so you see what we draw. Here we have it. Green points, red arrows, and they are dashed. So the red and dashed is for the table of arrows. And the arrows start in the point 0, and they go to ij. And j is I runs from I1 to 4, and j runs from 1 to 4. It's pretty clear. You know, if you press Control Point, you get here the full table command. So in the table we have this arrow, comma, and then we go to green, take a green pen, point size 0.02, and that means that's the proportion of the full graphic size. So in this case, 2%. And then we draw just a point at the location I, j, and here you see what happens. And the graphics command is putting all these geometrical primitives, as they're called, together. You can combine any graphics. So suppose we have a graphics P1, and that's the plot that we saw before, a combination of the cosine x and cosine 2x, where x runs from 0 to 2 pi, and the plot legends are the expressions. This ends the plot command, and then P1, and then we show P1, and we do some extra things. You see, we open a curved bracket here. We take the plot P1, and then we add the graphics of a blue circle. Plot range all and aspect ratio automatic, and this is what we get. It's a very nice combination of the two graphics, the circle and the cosine 2x and sine x plot together. In 3D, it becomes quite interactive, and then we use graphics 3D. Everything is interactive and can be rotated. And with interactive, we mean that you have a very nice interactivity with 3D graphics. Please read these very nice tutorials right here. I'm going to show you a little bit here in our own notebook. So suppose I make a table of just RGB color, that's the way we name red, green, blue color, with opacity 0.5. Opacity is quite strong, that means that it's a transparency. Transparency is 1 minus the opacity. And we draw a cuboid. And this is the P is the lower left corner, and P plus 0.15 is the upper right corner. And we do it for I, j, and k. I runs to 5, j runs to 5, and k runs to 5. You see, I don't have to specify I, 1, 5, as I can directly say I, 5. So I get 5 by 5 by 5 colored cubes. And now you see you can nicely interactively rotate it. And you see how fast the graphics on the Raspberry Pi 5 is. It's quite impressive. And you also see the opacity. If you make the opacity really small, let's say 0.2, you get very transparent ones. You only actually see the boundary lines. And if you make the opacity 1, there is no transparency anymore, and you have dense blocks. And you can easily, if you need some other color, suppose I start a new cell and I want some specific RGB color. How do I know what it is? Well, you look at insert and you type color, and then you can pick any color you like here from the palette. You can take them from the basic colors, or you can pick them right here, any one, and you can change the brightness right here. So any color you like, and then you just say OK, and then this is the RGB color that you like in your code. It's very convenient. Here's a Kleb surface, and the Kleb surface is a polynomial, x to the third, etc. And don't worry about the complex polynomial. What we're going to do is we make a contour plot 3D, and that means, and the contours are just for 1. So in 3D, this surface, this function, where it has the value 1, we let in x run from minus 2.5 to 2.5, y and z the same. We have no mesh on the point. Now you see the power of how you can modify any graphics that you like by setting the options. No mesh, the number of plot points in x, y, and z. So that means how many points do you calculate along the x, y, and z axis. You can change the contour style. In this case, we say we have a surface color that's a brownish-like color. And the second one means there is a specularity, and this is how much the specularity should be. Actually, let's have a look. And here we have it. You see the background is black, there is no box, and this is a beautiful graphics. And now you see the smooth motion, and you also see how very nice the lighting conditions are. And I must say that on the Raspberry Pi, this is a very nice way that the graphics unit of this machine, and Mathematica, is extremely powerful in generating this. You specify a viewpoint, no axis, image size is 500. It's quite comfortable. And if you look at contour plot, contour plot 3D, you'll find all the options to put there. And as I said, this is just a gentle introduction. It's a beginning. Have a look at the functions itself. Here's another one from the k-means clustering. Suppose we have 300 data points in 3D. So what do? We make the points in 3D and we call the function random real with values between 0 and 1. You see, this is a list from 0 to 1. And we have 300 triples. So we have x, y, z coordinates, and they are generated in the first line of this command. Then we make a graphics 3D, and we have the point 3D here. And this function we will explain in the next section is the function map. That means put the function point on every element of these point 3D, and there are 300 of them. Make the opacity 0.1, and then we have all these points in 3D, and we say we have the function find clusters. And how do we do that? Well, you specify in the options that the method should be k-means. This is all you have to do. So it finds now 15 clusters in these 300 points, and then every cluster you say, okay, map again, so do for every of these clusters, so do it 15 times, the complex hull mesh. Okay, how does that look like? Wow, we get all the points in 3D, and we see that we have now very nicely 15 clusters. And you saw the speed that was calculated in a very small time. And we have now an interactive way of inspecting these 15 clusters in your data. Of course, the data were random, but if you have real data here, you can do exactly the same. Some fun with a fractal, and that's called a Julia set plot. It takes a complex number with A the real value and B the imaginary value, and this I is the square root of -1. And you type it as escape I escape. You can also type a capital I, but this is the scientific notation. Plot legends should be automatic, and we let A, we manipulate it, as you see, we have here manipulate. And we manipulate A from 0 to 1, and we give it a starting value of 0.365. Same for B, also from 0 to 1, and a starting value with this. So now we have a Julia set plot, it's right here, with a manipulate, and now we can interactively say, okay, let's change. During the change, you see there is a very coarse approximation, but as soon as you finish, Mathematica calculates this all one by one. It's pretty fast and it's really nice. It's interactive. Here you see the plot legends, so that means the specific colors mean specific numbers. Data visualization, function visualization, and charting are extremely powerful. Maybe the most powerful visualizations that exist. Let's have a look. If we go to data visualization, let's make it full page. All the different plots that you can think of, list plots, list line plots, list step plots, list plots 3D, all of them have examples. You can copy paste from the documentation center, matrix plot, array plot 3D, feature space plot. It's extremely powerful. It's fast. It's just plain English what these plots do. 3 plots, bubble charts. It's quite amazing. And wavelet visualization, color space visualization. It's almost infinite. Let's go to function visualization. Here we have the same. Not only the simple things for 1D, plot 3D, contour plot as we saw before, contour plot 3D, density plot. It's very impressive. So have a look and play with all these functions. And you will see that it is far more powerful than any other visualization package you have seen before. And the last one is charting and information visualization. Same thing, have a look at the documentation, and any statistical visualization in pie chart or bubble charts, in 2D, 3D, sector charts, histograms, it's all there. And all the 3D are interactive. You can manipulate them in 3D. And suppose you want to have a bar chart in 3D, some very simple example here with the range 1 to 5, the numbers 1, 2, 3, 4, 5. And the chart elements you want to have cylinders. Okay, just add cylinders. You can have it here. And now it will take a bar chart in 3D with cylinders. And here you have them, and you can manipulate them in 3D. This is a parametric plot 3D, and that means you have in 3D, this function is the u and v, this function is of u and v, and this function is of u and v. And we make u and v, u from 0 to 2 pi, and v from 0 to 2 pi. And this means we get now the change with cosines and sines in this function, no mesh. And there's a plot style that we say, okay, we make it red, opacity 0.3, and we give it a texture. So you will see that these are two intersecting tubes. And now you see another very powerful thing. You can make a texture, and any texture you like, you import any image as you like, and you could put now any texture on a graphics, which is nice. You see the opacity is 0.3, so you can look through, but no matter what you put on the images. Here we define some vertex coordinates, and this means these are the coordinates of a square. 0, 0, 1, 0, 0, 1, 1, 1, and 0, 1. And these are the coordinates, the same thing from a cube. If we now put the texture, and I say, okay, let's take a wood texture, and then make a polygon from all these points that constitute my cube in 3D space, and I put the vertex coordinates for the texture, that means where does the texture need to land on this, and I make these squares, it's called the vertex coordinates, VTC, and I make them 6 times, so I do it on all the frames. This is all I have to do. So you first have to define them. Now you see, otherwise you get an error message. You saw it was blue, and that means it was not yet defined, so I should have been warned. It's good to show this. And now you see, I make a cube, and I have a wooden block here by just a simple graphics command that you say, okay, first with this texture, paint a polygon along these coordinates and put a texture on these vertex coordinates. Do it 6 times. And here you have it. You see, it's fast, it's high resolution, it's interactive, and it's a very small set of lines of programming. And now we go look at functions and functional programming. This is the heart of the power of Mathematica. It will be quite different though from object-oriented programming. I'm going to discuss pattern matching, functions, and list manipulations. Let's start with pattern matching. Well, pattern matching is actually change something into something. If you have a pattern, I have a series of numbers here, and I want to change the 7 into the string 7. And this goes with the command replace all. And of course it does it. You see I have 2 7s and they are now replaced by the string. This replace all is used a lot. And functions that are used a lot have a shortcode. /points is replace. So if I now say I have this string, replace 7 by the string 7, that's a much shorter way and it reads easily in English. Replace the 7 with something else, in this case the string. If you have more replacements, so you have this string, you say, okay, replace the 7 in the 7 and the 1 in 1, you just give it a list with curly brackets. Then you can put as many things in there as you want. And now you see I have replaced all the items with 7 into the string 7 and the 1 in the string 1. Here we have the underscore, as we said, it's any pattern. So if we have here a number of things, so here we have c to the power of 2, the digit 2, then w to the power of 6. Replace anything to the power of anything. So this means a exponential form, and it doesn't care what it is, and it doesn't care what the exponent is. Replace this by z. So this means you have now really a pattern, something to the exponent of something. Okay, let's have a look at functions. Functions are crucial. And functions are actually the verbs in the language. You do something. Here we have a function, test if it is no, it's a function, give me the prime. The 5th, the 6th, the 7th, the 10th prime. And I define it as follows. If I say f of 10, then I get a 10th prime. So function is with square brackets, and it is a function of something, and this is the variable. And the variable can be anything, but we name it x, so we can use it on the right side as x. So we take the prime sign, prime of 10, that is the 10th prime number. And is clear, but a semicolon is means a delayed assignment. So it is only executed when it is called. Let me give an example here. I have the function dateList. And dateList, let's first do dateList. Function, what does it do? Okay, it gives me the exact date, year, month, etc. So if I make now D1, I assign it with is, the dateList, and D2, the delayed dateList. I have semicolons here, so there's no output. Now let's ask what gives D1. What does it give? Okay, it gives me the dateList at the moment that I defined it here. D2 is the current time. So because it is only executed at the moment that I call it, D1, let's call D1, it's still the same as before here when it was defined, so it didn't change at all, but D2 is now the time at this moment. You see, it's later. So functions you mostly use, or almost always, with a delayed assignment. This is a second method, because we don't need this f as a function. We could just say square something. So we have here the function, and now we have a machine. We see a function as a slot machine. You put something in the slot, and you get something out. You put a coin in, and you get 3 coins out, or the square of the coins, or whatever, any function. And the slot is indicated with this hash sign. So the slot means put something in, and this means it's a function. So the slot and this ampersand sign always go together. So this whole thing is the function, and it's called a pure function because it doesn't have a name. This means square something as a function. And then we get the function bracket, do it on 12. So this means square the number of 12. We can even make it even shorter, that we say, okay, we have the mathematical definition of a function. X is replaced by x squared, and the function that does that is defined by this. This means it's a grouping, so this whole thing is the function definition, and the call is with the square brackets. So this does the same. And you enter this specific symbol with, as you expect, escape, fn from function escape. And here you see a nice tutorial on functional operations. And if you see these functional operations, there are quite a few. You can change all kinds of function names. And this is for the people who really like to go a little bit deeper in what do these functions do. You have inverse functions, etc. It's extremely well documented. We go to the last part, and that's list manipulation, extremely powerful. In the Mathematica, you don't want to have, let's say, all the bookkeeping, if you have a list, you don't need for loops anymore, but you just say map this function on P, Q, and R on all elements of. And you can say map the function, and now f is still defined. It was the prime function, so I should say clear f. Now f is blue again, and now I can see f has no specific function anymore. It's instructive to see what happens if you keep defined definitions. But now we have f of p, f of q, and f of r. And the shortcode is do this for all / add. So now we have function. So this means f is mapped on all elements of this list. So if you have, for example, a random real list, and these are triples, 1000 triples with values between 0 and 1, random real. Now you just give any of these 1000 xyz triples, map the function point in front of them. So you get 1000 point functions. Okay, nice. And in graphics 3D, you plot them and you see it goes really fast. And on the Raspberry Pi 5, it's also immediate. Another function that's really powerful is, let's have a look at this list. You see it has a head and then elements. So the list 1, 2, 3 is just defined as the list. Well, you can take off this head list and replace it by something new. And that goes with the function apply. And the shortcode for apply is add. So if you now say put plus in front of 1, 2, 3, well, what does it do? It, of course, operates the plus, and you get very fast, no matter how big this is, it adds them all up. So suppose you have a function here, factor integer faculty 20. Faculty 20 is a big number. Let's see how big it is, and do copy and then paste. It's quite a big number. Let's see what a factor integer is doing. Okay, it gives me 2 factors of 18, 3 of 8, 5 of 4, etc. So I have a whole thing of them. If I want to write this as 2 to the power of 18 and 3 to the power of 8, I can use the function superscript. So this means 2 to the power of 18 to 18. And now just say, apply superscript for this whole set of double functions. So we have now applied superscript in front of it, but it didn't work because superscript should not be done on this whole list, but it should be done on the sublists. So that's not level 1. That means we only need to do it at level 1. We can give a list of levels here, and we don't specify a number of them, but only 1. So now I have done it, sorry, apply the superscript on this whole set, only on the first level. And now you see I have the nice scientific notation. You can also do it by saying, okay, I have a pure function, something, that's the first element, to the second element. And the first element is, of course, 2. And this is the second element, 18. And do that. So this ampersand means it's a function. The first element to the power of the second element. But don't execute it. If I take 2 to the 18th, it gives me a number, so I say hold form. Just don't execute it, but show it as the form. And then exactly I get the same. You could also do the thing that you say, okay, with pattern recognition, you could say, okay, every pair that occurs here, replace it by, and this is now a pair something, comma, something, so the underscores are the important things. This one is called A, the first of the pairs, and the second of the pairs is called B, but the underscore means something, comma, something. Replace it by A to the power of B. Okay, let's do it. Very nice, it did it, but this 2 to the power 18 was evaluated. So it's better to say hold form. And now we see we have done functional programming in the sense that we say, okay, we have changed, replaced, and the replace is done by /point, any pair, in which I call the first A and the second B, to A to the power of B, and don't evaluate it, but just show it. Okay, another one is map apply, and that's a combination of both. So if I have a list here, but it is a combined list, and I do map apply f of them, you get f of the first one to f of the second one. And you already see that the combination of these functions give you extremely powerful manipulation of data. You have to work with it a lot, you have to exercise, and there are lots of examples. And the shortcode for map apply, this means change the heads, but do it for all of them. So you understand the name, map apply. And this is triple add. You can also say F map apply. So change the head for all of them, change the head for A and B, and change the head for C and D, and there you go. If you map apply superscript on this function, you see you immediately can do it. And now you see how incredibly powerful these commands are. You can also write it shorter by map apply and write it as 3 add signs. And here you have the function hold form, and then you do it. This is a function. Do the first one to the power of the second one, and now you do it on this. Okay, the last ones are thread and map thread. Well, thread means that you just mix two, interweave two lists. So ABC and XYZ, if you interweave them, then you say, okay, I take F on the first of each, the second of each, and F on the third of each. So this is another way that you can just make two lists interwoven in a very nice way. And it doesn't matter how long this list is. You can even do this on much higher dimensions and at different levels. So if I have, let's say, I change ABC into 1, 2, 3, you can say, okay, that means A goes to 1, B goes to 2, and 3 goes to 3. So now I have 3 replacement rules made by this single command, in which you say, okay, I have a whole set of definitions or keys, and they should point to values. I can now, with thread, make immediately all the replacement rules or the assignment rules, association rules. And map thread does the same. That means now you map it on all elements of. So you have f of A with X, f of B with Y, etc. Suppose I have an eigensystem. This is a small matrix. And this matrix, let me copy it. I can show it here. By the way, if I want to show this matrix, I have it here in a cell. I can also say to the cell, convert to traditional form. And now you see, if you want to convert it to the form that you recognize in your textbooks, you just change the text. There is a little wiggly indication on the cell bracket here. But the eigensystem calculates eigenvectors and eigenvalues and eigenvectors. So now you see, if I do this, I have 2 eigenvalues, 5 and -1, and I have 2 eigenvectors, this one and this one. Now, if you say you want to divide the eigenvectors 1, 1 by 5, you just say, okay, this one is the second one, and this one is the first one. So make it a function, and thread this on this function eigen. And now you see, okay, I have divided this vector by the eigenvalue divided by 5, 1 over 5, 1 over 5, and this one divided by the other one. So in very short terms, I can manipulate data in quite complicated ways. It looks a little bit artificial now if you see this for the first time, but once you get used to this, it's extremely powerful. And just my strongest advice, play with the endless examples in the documentation. They are nice, they're illustrative, and I don't have time in this short, not so short, but play with the endless examples in the documentation. In the examples, there's always at the end a neat examples section where you see, hey, some striking and fun examples. Okay, symbolics. And this is what Mathematica is famous for, of course, and the name Mathematica says that it is mathematics, but as you know, Mathematica can do far more than just symbolics. In numerics, it is faster than many other programs, and it can do geographics, it can do neural networks, it is incredibly versatile. But symbolics was the first powerful thing in which actually the reason to develop Mathematica. But be aware that Mathematica is an immensely huge and broad programming environment today, including financial, chemical data, you name it. And we're going to show you more details on all these other fields as well. It has a large knowledge base, huge number of databases are immediately available. But now let's focus on symbolics. Suppose we have this integral here. Let's calculate it. But how do you enter an integral like this? Let's do it again here. What we could do is we go to the palettes and we take the basic math assistant. You see we have the palettes here. And we can add all kinds of things. In this case we go to the advanced tab. And we click here on this integral. And now we have the integral. And if you use the lower one, we say, okay, minus escape, inf, escape. That gives me this one. The upper one is escape, inf, escape. This is the E, and that's escape EE. To the power of means control head. And now minus x. And again to the power of control head. That's just above the 6. And then 2. Now I move my cursor to the right. And I go here. And in this variable, I just say x. And now we have it. So no matter how complex this is, you can now add it using the palettes or using the escape and control keys to add anything you want. If you want, for example, here, Control 2, you get the square root. Control Z, it's done. If you want the whole thing, square root, you say Control 2. And then you get the square root of this. So anything you like, if you want to remove the square root, just put your cursor here and remove it. And the output is a symbolic value, it's the square root of pi. And this is infinitely precise. So if you want the numerical value of the square root of pi, you just say copy and put it in the new function. And now you get the numerical value of the square root of pi. And if you want this in 100,000 decimals, you get it in 100,000 decimals. And it is immediate. It's a lot. On a laptop, I have a nice laptop, I was able to calculate 1 billion digits of pi. Well, of course, the Raspberry Pi is not fast enough with such big numbers, but you see that in this case it's already quite impressive. And solving an equation is exactly as you expect it to be. You put solve with square brackets in front of an equation. An equation is to the left the part, and then double is 0. And the double is not a single is, that means it's an assignment, but this means is equal to, it's an equation. And we solve this for x. Well, it's a famous equation that you know from high school, and here we see the solution. So x is one solution, here is x the second solution. To visualize that, we can make the intersection points visual, and this you see is a circle, and this is the parabola. By the way, to make this yellow background, what you do is you just select this part and you say, okay, format background color, and you give it any color that you like. So you can do all kinds of nice things in your text. So let's solve this equation here. This is equation 1, and this means logical AND. So we have one equation and the other equation, and we solve them for x, y. And again, this is a list, so between curved brackets. Solve is with a capital because it's an internal function, and solve has square brackets. So let's solve it. And what do we get? We get 4 sets. This is the set x, y, the first one. This is the set x, y, the second one. And you see x is, with an arrow, is assigned to this solution. To visualize them, I can do a contour plot of these functions. So I take x squared plus y squared is 1. So the function in 3D of x squared plus y squared. And then what surface? Well, the function where the function has the value 1. And this second order function where it has a function 0. It's a set, it's a list, so that's why it has the curly brackets here. This is the range, x from -1.5 to +1.5, and for y the same. And we combine two things. We have the contour plot, and that shows us the circle and the parabola. But we also want to have graphics. We combine them with the function show, and show ends here. And what do we have then in graphics? Points that are red with point size medium, and we map the function xy onto points. So x/point means map. So all these points xy get the value given by these points. So x becomes this, y becomes that, and that is filled in this set. So we get here the coordinates x and y 4 times. And then we put the function point in front of it. Let's have a look what it does. And immediately we get the function. And you nicely see we get the circle, and the tooltip gives us x squared plus y squared is 1. Here the tooltip for the parabola, and here we see the yellow point of the red points of the intersecting. Even highly complicated integrals can be solved, and Mathematica is really famous for whatever integrals you put in there. Suppose you have this crazy looking formula and you let it calculate. Well, it takes a while, and of course you cannot do this by hand, and it's not likely you will express an expression like this, but it gives the power of numerical capacity, of the symbolic capacity that Mathematica can do. Suppose you have an integral like this, and you see I get 3 terms here. First this one, this is the second one. And if you take now, int is the output, so this whole thing is now called int. If you take the derivative, it should be the same. But hey, it's not. Well, because all these terms have not been simplified yet. So if you do the simplification, so simplify this, and now very nicely we get this. Simplify is really powerful because it takes all kinds of rules, lots of rules actually, to make this expression as simple as possible. Well, there are very nice tutorials. There's a really nice tutorial, algebraic calculations, and it's recommended to go through this. There are lots of really nice suggestions and tips, and it takes you at the hand in many pages on how to work with these algebraic calculations. And on YouTube you see, of course, lots of examples, most of them written by hand, because if you don't use Mathematica, you have great difficulty in expressing all these divided by exponents, etc. But in Mathematica you can do this now so easily. So suppose you see a YouTube with this, how to simplify this, you just say Mathematica, and now you know how to enter this with control head, etc. And you simplify this, and you immediately get this, and that's the answer. Neural networks. The best way to start neural networks with Mathematica is to look at the Wolfram Neural Net repository. That's a public resource that hosts an expanded collection of trained and untrained neural network models, suitable for immediate evaluation, training, visualization, transfer learning, and more. Let's have a look. It's a website, and let's make it a full page. A little bit bigger. And you see that we have lots of neural networks here in audio analysis, classification, and trained on handwritten digits from MNIST to image competition data, efficient net, different versions, V2, gender prediction, inception V1, and it goes on, and all these networks are fully programmed in Mathematica, can be downloaded as a notebook. Let's just take an example, and we look at inception 1. You see that it gives a nice description. It's a parameter count of almost 6 million, train size 24 megabytes. And you see here download the example notebook, then you have the full code, how it is programmed. And here are nice examples. It's all in Mathematica notebook form. You load it as net model, and then you give it a name, inception V1. It will load, and here you see the whole network, all the layers. And in this documentation, you have lots of examples. The first one is, of course, the basic usage, that you say how many salient objects are there. So you see net model loads this data, and then you open brackets and you put an image in there, and it says 2. Well, this goes on and on. It gives you probabilities, net information, etc. Let's have a look at some applications, and let's have a look how many are there. If you give net model without any argument, let's do it. It reads and now we see that we have all the titles of all the networks that are available. And it's quite a lot. And all of them have specific uses. Let's have a see how many there are. I see already 155 if you take the length. Currently there are 155, but this set is continuously updated. Let's look at 2 specific examples. The first one is image colorization, trained on ImageNet. You know that ImageNet is a huge data set, more than 1.2 million images, and this network can colorize images. So first we go see what is the description of the object, and then we use the function resource object. So it looks at the resources, and it downloads it. You can open it, and it gives you the name, what is the type, it's neural net, colorize a grayscale image, how big it is, and how it was trained and when. It's an older network, 2012. It inputs an image, and if you download the network itself, we go have a look at the network, and it's called ColorNet. This is our own name because it starts with not with a capital, but of course the function itself, net model, starts with a capital, and as familiar, square brackets open, and then the string for the title. And now let's have a look, because this was closed, and we have the network here. It's a net chain. It means it's a chain of all the layers. And this is just beautiful. Here we have a very nice representation of the input is an array size of black and white image, 1 byte per pixel, 224 by 224. That's the standard input size. If you give it another input size, the encoder takes care of it. And you see that from the other layers, it's carefully indicated how they look like. So the first convolution layer did 64 levels of 224 by 224. Here it is 112 by 112. Here it goes to 128 by 112 by 1212 in this conv 2.1. And if you go further down and you look at all these layers, you see there are quite a lot of layers. And the output is 2 images of 56 by 56. If you click on a layer, for example, on this convolution layer, you get all the parameters from this specific convolution layer. The final convolution layer, if you click on this one, you get this specifically. Transpose layer, you see exactly what is the input, what is the output, and here is the output layer. It's an array of 2 times 56 by 56. So it's a lower resolution than what we put as an input. That has some consequences. So if we take the image as an input, the black and white dog image, we work in the network works in the LAB color channel space. That means it's an L channel for luminance and 2 color channels, A and B. The color channels are at a resolution of 56 by 56. So if we need to combine that with the original luminance level, we need to resample. And then, only because we have only the 2 color channels, add the luminance channel. So that's what we do with net evaluation. So let's see what happens. We first take the luminance level, the luminance layer, that's a single image. We do that by color separate. So we take the input image and we take layer L. Then we're gonna do the array sampling, and we do color net the luminance level because that's now color net is the neural network that is applied on my data. So the black and white data goes in and 2 color channels come out, but this is 56 by 56. So we go do an array resample. But to what dimension should it be resampled? Well, comma, and then we specify the dimensions here. First, we take the image dimensions of the image. That's 224 by 224. Then, this is something quite typical in many computer languages. If you have a matrix, the first element is in the upper left level. But if you take graphics, the coordinate of the origin is mostly in the lower left level. So quite often you have to reverse the coordinates, and in this case we do that too. So we take reverse. This add means we apply it as a function. Then we add to these dimensions, because if you really want to see what happens, you can work from the inside out. So let's see what happens if we do this specific statement. We copy this and we take it out. We see, okay, we take the dimensions of image, we reverse them, and we put 2 in front of them. So now we get 2 layers of 224 by 224 pixels. And that is the set of how we need to resample it. If we have resampled this to 224 by 224, then we do a prepend and we plug the luminance in front, L, and we have the other 2 as AB. So we run this, and now we can see what the network does. So we do a net evaluation, and color net is called. You see how fast it is, even on the Raspberry Pi. We have a beautiful colorization. So if you have a whole set of old images and pictures from a long time ago, you can now nicely try to get a lot of colors back. And the second application is CycleGAN, photo to Van Gogh translation. Well, interesting. How would Van Gogh plot specific images? And you see already the image we're going to give Van Gogh an X-ray scanner in a radiology room. We have never seen this, but let's see how Van Gogh would have drawn this. So we're going to take a network, and the network is called CycleGAN photo to Van Gogh translation. The research object gives us the full translation, turn the photo into a Van Gogh style painting. It has learned lots and lots of paintings and photos from Van Gogh, and let's see what we can do. We download the network. It's not too big, 11.6 megabyte, and we open the network again, and we see that there is a lot of layers. In total, we have 33 layers, and all these layers, they can be described one by one. We have a padding layer, a convolution layer. If we look at the back, we see nicely what this convolution layer does. If we take this padding layer, you see layer 31, it has all these parameters, and the output is an image. That's 256 by 256. Okay, so let's have a look at the input image. We take this image, And we already saw in the end that the output image is a square image, so we need to resample the input and of the input image. The network is adapted to the new input and output image dimension by changing the encoder for the input and the decoder for the output. But in Mathematica, it's always plain English, so we call it the net encoder. And what does the net encoder do? It takes a parameter in the form of an image with the image dimensions img. And then the net is changed because we need to have this encoder embedded. And then we say, okay, we do a net replace part. Net is the input, is the network that we have just read from the net. And then we change input to layer input to the net encoder, and the output will be the net decoder. Okay, so let's execute this statement. Now it has done the surgery. It has now taken these new parts in, and we see that we take new as an input the size of the original image, 493 by 958, and we have as an output also 496 by 960 as the output. So let's see what the network does. We ask it to do the Van Gogh net, and even on the Raspberry Pi, it takes a reasonably short time. It'll be about a minute. And now we see, or less, and now we see what Van Gogh does. And this is pretty impressive. This is really nice. That means that every edge and stroke and corner and element in the image that the network has found has now been converted in a Van Gogh style. The colors have been changed, and it's a pretty Van Gogh drawing. And it may, of course, never have been seen by Van Gogh. To finish this small introduction on neural nets, and there will be many more tutorial YouTube movies coming up with all the notebooks, so check it out in 21st Century Coding. The best book I know on, not a book, but a computational essay written in Mathematica with all the notebooks is written by Etienne Barnard. It's called Introduction to Machine Learning. It's outstanding. You see the website here. Make it a little bit larger. It really takes you by the hand, and it has all kinds of machine learning paradigms on classification, regression, how it works, clustering, distribution, but also about surgery and encoders, decoders, autoencoders. It's very, very complete, and everything is a Mathematica notebook, and you can just do it step by step yourself. If you look at the book itself, you go to this website, and you see Etienne here. He was the scientist that made the machine learning in Mathematica. For 7 years, he worked on this spectacular implementation. And here you see all the notebooks and the. So if you look at clustering, you get very nice. Here you see all the code can be downloaded, clipped to your notebook, where you can download the whole book as a notebook. And it's incredibly easy to learn. Of course, it takes you a couple of hours, but if you compare it to many other courses, the power of what you have here with Mathematica is incredible. So check it out.